Hey everyone, welcome to Monologues. This time we'll be looking at executing a sorting problem with ALP program. ALP means assembly level program or assembly language program. When we think about sorting, we have learned a lot of sorting algorithms like insertion sort, bubble sort, selection sort, quick sort. We've learned so many algorithms like that, out of which we'll be using bubble sort because in ALP bubble sort is the easiest to program. So we'll first see how bubble sort works and then we'll get into coding. So let's see how bubble sort works. By looking at the figure, you can see an unsorted initial array of 5 elements with the elements 5, 3, 8, 4, 6. Now our aim is to bring this unsorted array into an ascending order using bubble sort algorithm. So let's start. Step 1. Now we are looking at the first and second element, which are 5 and 3. Now we are comparing between 5 and 3. And we find that 5 is greater than 3. So what do? We swap them. Now we get 3 and 5 in the first two element positions. Now in the second step, we compare the second and the third element, which are 5 and 8. From the algorithm, 5 is less than 8, so we don't have to swap. We'll jump to the next position. Then we'll check between third and the fourth element, 8 and 4. 4 is less than 8, so we need to swap. We swap them. Now we check 8 and 6. 6 is less than 8, so we swap them. Now we get 3, 5, 4, 6 and 8 at step 5. Now, as you can understand, we've traversed through the array once. Now imagine us doing the same for 5 more times. We'll check the same way once more and again for 5 more times. And by this algorithm, we will get an ascending order array. So bubble sort is pretty easy, and I'm pretty sure that you can understand how it works by looking at this figure. Alright, so we have opened our Atmel Studio environment, which is basically an IDE to do our programs in microcontrollers. So we're gonna start a new project. We've chosen assembler, and we can browse here and go to the preferred location we want to store it. Give it a name. Let's say ALP sorting. Let that be it. And click OK. Now we've come to a device selection page. We'll be using the instruction set of ATmega128, so we need to select that specific device. Okay, so now we can actually start to code. Okay, this is just the initial setup. We can delete this, we don't need this. We can delete it. So yeah, in ALP programming there are certain things that we need to know. Now .cseg means it is the code segment. So in program there are two segments that we can write, the data segment and the code segment. Because we are just doing the simulation, we don't need any extra data to be initialized. We are just directly going to the code segment. So .cseg would do that. Now we'll go to the next line. Now that we are giving the origin, that .org, putting 0x00 as the origin. Now that means the starting address of our code in the memory location. Because we are doing the simulation, doesn't really matter, but when we're actually doing we are actually burning the R code to our microcontroller. That matters because we need to know where the code is, where the data is. Such address spaces matter a lot. Okay, now we can go down. Now, as we discussed, we will first create a loop to traverse through our array. So let's do that. No, before that, we need to know about the pointers. I hope you guys know about the pointers. So we'll be using the X pointer, which is basically the registers 26 and 27. So we have to first initialize our memory address value where we are going to store our array, that the array that we need to sort. The first element address should be given to the pointer. So let's do that first. We'll start LDI 26. We are giving that the value 0, 0. And next line LDI R27 0, 1. So right now R27 acts as the MSB and R26 acts as the LSB. So the address that we are directing our pointer X to is 0100 in hex. So we're using our X pointer to point to the address 0100. I hope you guys understand that part. We'll give a comment. X with the value 0100. Okay. Now we have initialized our pointer value and we are as of right now pointing to the first element in the array. Now we are going to put an inner loop. Okay. Now what we are going to do here is store the value in the memory to some registers so that we can manipulate them. That means we can do our compare instructions. So we need to store the value at the first element that is being pointed by X to a register R16. Let's do that. We are loading directly from our memory to the register R16. X plus. Now what does this X plus mean? This means post increment. So it will first store whatever value the X pointer is pointing to the R16 register. Then later, after it has been stored, it will increment the X pointer. We can actually provide a comment for that so that we can understand it better. Loading the value pointed by X first to R16 and then increment X. By incrementing X, we are actually incrementing the R27, 26 registers. Okay. After that, we'll do the same to R17, a new register, so that we can get the next number. Now we will not be incrementing our X pointer because we don't want it to go further from this. Okay. This also will comment. By X to R17. That's it. Now what should we do after this? Now we have two values at R17 and R16. So after this, what we need to do is compare both of them and get a result from that comparison. So we'll use the instruction CP to compare between the registers R17 and R16. Now what does R17 hold? The second number, and R16 holds the first number. Now, so we are comparing between first and second elements. Now after this, what do we need from this? If the value at R17, that is the second element, if the second element is smaller than or less than the value at the first element, we need them to swap. So we have a branch instruction which is BRLT, which means branch if less than. So we need to it compares to the compare instruction just before this branch instruction. So it will branch if that compare instruction gave a less than result. So branch if less than to some other function called swap. We'll be writing the swap code later, and we are giving a label back. Now why are we giving a label back? Because we need to get back to this code after we've executed the swap operation. So we'll give a command, go to swap operation if less than. Okay. Now after we've done the swapping, like after we have compared once, we need to do a decrement of a counter value. Now before that, we'll give wait a minute. Okay, so here before we get into our loop, we need to give counter value to some register, let's say R18. Now we load R18 with the value 09. That means we have 10 elements. So let's comment that too. Loading counter value 9 for inner loop. Now we need to decrement this R18 so that the 9 will become 8. Now why have we given 9 instead of 10 to count for 10 elements? Because we are decrementing and checking whether that value comes to 0. So 0 to 9 means 10 elements and 10 iterations. So that's why we are giving 9 over there instead of 10. So we need to decrement R18 right now, and then branch if not equal to 0. This is what this branch instruction means, BRNE. That means branch if not equal to 0. To where? To the inner loop. Yeah, because now we have to traverse through the array 10 times. So we have to traverse through the array 10 times. So if the counter value is not 0, we need to go to the next traversal, to the next iteration of our traversal. So it's branch if not equal to 0 to in loop. That is continuing with our inner loop. Okay, now we have created our inner loop. Now after this we'll go down to some location and create a swap program. So the name you given to a swap is SWP. Now this is just as a go-to label. We're giving a label SWP. Now what are we trying to do over here? we need to store back the values in the registers R17 and R16 to the memory locations that we got them from, but in the reverse order because we are trying to swap. So right now X is pointing to the second element, so we have to swap the value at R16, that was our first element, to the pointer pointing to the second element, that is X. So we are pointing, no, so now we are storing the value, the R16, which was the value in the first element, to the second element right now, and then after that storing the value at R17 to where? To minus X. Why are we putting minus X? Sorry, hold on, pardon me, the syntax is wrong. It's store minus X to R7, store R17 to minus X. This is how the syntax is. Sorry, R16. So why are we putting minus X? Now minus X, instead we've seen X plus earlier, that is post increment. This is pre-decrement. So we'll decrement the value at X first, then store. So that's how pre-decrement works, and we are just simply swapping. I hope you are getting the logic. Swap. Now we have decremented the X value, but when we do it the next time, when for the next iteration, we need the X to point to the second element so that we can compare the second and third element. So we need to increment that X value once, because we have been decrementing it just the instruction before for swapping. Now but we can't do increment X, we need to increment the register that holds the X value. So R26, we need to increment R26. Now what you have to do, go back to our main loop, R jump, which is just the normal jump function, and we are going back to where? To back. That's why we have given that back instruction, back label way in our inner loop. So that's it. Swapping will work like this. This will work. Now what we have created right now is an inner loop to do 10 iterations and go through our array once, but that is not enough. We've seen the bubble sort algorithm before, and we know that is not enough. We need to do it 10 more times. So how can we do it 10 more times? Easy. We can just put another outer loop and do it 10 more times by putting a counter. So we'll do an LTI, use a register R19, give it the value 0, 9, and give a label to repeat, out loop. That's it. And after we finished through our inner loop, we will decrement our R19, check whether that is equal to 0. If it is not equal to 0, go back. That's it. So we finished our outer loop also. Now because we need the program to stay still until we check our results, because the microcontroller works at a different speed, like faster than our eyes and cognitive ability. So we need to make it halt for some time. So we'll just put an infinite loop where it will do nothing. So we'll put an end label and put a R jump to that same end label, which will be doing nothing. So we'll just make this little cleaner so look good. So basically that's all it is. We'll do some more commenting. This LDR1909 was a outer loop counter. Outer loop counter will be decrementing the same. The R18 was array team was decrementing inner loop counter, and here it was decrementing outer loop counter. So from a logic, this should work. We'll be compiling it right now and checking whether it has any bugs. So we have to do the build option, build solution, and yeah, we have certain errors like what? Okay, invalid number. Okay, because we are doing we have to shouldn't give 09. If you are giving 09, we have to specify that this is in hex value. In hex value will be given by $sign. That's the only thing. Okay, we'll check again. Build succeeded. So this is the program that we've written. We'll go through the program once again. So this is .cscg, which is basically the code segment. We are specifying the code segment, and .org 0x00 we are specifying the origin address of our program. That's it. Now what did we do here? Coming to this link, in a loop we are storing the elements pointed to by the pointer x to our registers R16 and R17. Then we are comparing those two registers, and we are just branching to a swap function if the first one is less than the second one is less than the first one. And coming back, then decrementing R18, which is the inner loop counter. Then if it is not equal to 0, we branch to inner loop and repeat the same functions. And after that, we'll check whether the outer loop counter has been reduced to 0. If it is not, we'll go back and repeat the entire thing once more. So we are traversing through a 10 element array 10 times. So that's how it works, and this is the swap program, and I hope you guys have understood it. Okay, so building again. So we have built it, the build is succeeded, and now let's go to our debugging mode. Let's select simulator as our debugging mode and build once more. Okay, go to debugging mode. Now here we have our memory locations that we are for simulation. So this is a program flash, which is our program memory, so we don't have to do any manipulation for that. It will mess up with the program. So we need to go to the IRAM, which is the internal RAM position. This is where we will be typing in the values. See, we have 0x0100 0100. This is the first address that we have pointed to by our pointer x. See, R26 is 00, R27 is 01, which is 0100. Here, same thing. Now we'll give some random values. We'll give some A, which is the hexadecimal equivalent of 10. We'll give 5, 8, 7, 4, 1, 3, 2, 6, and 9. Do we have 10 elements? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 elements. Okay, it's all set. So we'll debug. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0A, which is the hexadecimal equivalent of 10. We have gotten one unsorted array into an ascending ordered sorted array. So our program works. Everything is fine. We are all happy. Now we can stop debugging and go back to the code. Now, if we want to make a descending order array, what we can do is change this BRLT, which is branch if less than, and change that instruction to BRG, which is branch if greater than or equal to. That is BRG, branch if greater than or equal to. Let's see whether that works. BRG. We'll build again. Build is succeeded. We'll go to our debugging mode. Put some random values again. 1, 5, 4, 3, 2, 6, 7, 9, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 numbers. Okay. So we stored our unsorted array into our data memory, and let's go to debugging mode. There we have it. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have our descending order sorted array. Now we had to use a different instruction, which is BRG, to get the same result. Now, without doing anything like that, like with the same BRLT, branch if less than, our old program, the first program that we wrote for ascending order, with the same program, do you think that we can get, by without using any new instructions, like making some tweak, can we get a descending order array without using any new instructions? With a little tweak, can we get a descending order array with the program of an ascending order array? Can we do that? What do you think? If you can think about it, just pause the video right now and think about it and try to find a solution. And I have a solution. You could get a different solution. Whichever works is fine. That's all there is in programming. Whichever works, that we have to just get the job done. So whichever works is fine. I have a solution. So if you have to think for yourself, just pause the video and think for yourself. And if you wanna do it by looking at my solution, just this is my solution. When we are comparing the second element to the first element and see whether it is less than. We just have to reverse that order. Compare R16 with R17. Compare the first element with the second element. If the first element is less than the second element, swap them. So the greater element will come first. That's it. We'll check whether that works. Build solution. And we have built it. Build it succeeded, no problem. We'll go to our debugging mode. Yeah, we have to give some random values like we did last time. 5, 4, 3, 2, 6, 8, 9, 7. Is that 10 numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. We'll debug it, run the program. What do we have here? We have the descending order array. So that's it. We have achieved the descending order array without changing any, means without adding any new instruction. Just by doing a little tweak, we have achieved descending order array. So that's how it works. So that's how an ALP program works to sort an unsorted array using bubble sort algorithm. I hope this video is helpful to understand the logic. I mean, there are different instruction sets for different microcontrollers and microprocessors. You can write any program, any ALP program using those instruction sets from the data sheets the company provides. But all you have to need is understand how the flow chart works, or how the flow of the program works. So I hope this video helps you to understand that flow, and thank you for watching the video.